All right, welcome to the third lecture of Chemistry 51C. I start my lectures by talking about things that I've seen recently, and I just ran across an article in Google News that talks about compounds that are hot and compounds that are cold, and I thought that was a cool article. And let's go ahead and talk about the organic chemistry that's behind that. The article was talking about something called transient receptor potential channels. And anytime you've tasted something that is spicy hot or is cooling to your palate, that's because of compounds that are acting on these receptors, or at least for the most common cases. So one example of these receptors, they're found in many different cell types throughout the human body, brain, peripheral tissues, but also in the oral cavity, on the tongue. And so one of these examples of a receptor, or it's not really a receptor, it's an ion channel that you find in the membranes of cells in your tongue, is called the TRPV1, transient receptor potential channel V1. And those are activated by heat. Temperatures above 43 degrees Celsius cause a conformational change that affects ion flow. And conversely, there's another very particular channel called TRPM8, transient receptor potential channel M8, that responds to lower temperatures. So when the temperature goes below 26 degrees, it has an effect on ion flow through that channel. And what's cool about these channels is that they're not only affected by temperatures, not only do they serve as a thermometer for the mouth, they also serve as as receptors for small molecules that can affect their opening and their closing. So one molecule I think everybody is familiar with is the small molecule capsaicin. And when I say small molecule, that's for biochemists, small relative to proteins or DNA. But this organic molecule called capsaicin that you find in chili peppers or habanero peppers or ghost chilies, this small molecule acts on this receptor and affects the opening and closing, which affects ion flow through those, and ultimately affects the sensation of heat. And anytime you've tasted something that's got cool peppermint or menthol, cool menthol flavoring, like fresh mint leaves, those contain a small molecule called menthol. And menthol also binds to this TRPM8 receptor, this channel, and affects ion flow through that channel. And if you're really interested in small molecules that affect biological systems, you really need to send a synthetic organic chemist in there to go design something potent. Menthol is not a very potent molecule. It takes a ton of this molecule, high concentrations, to affect ion flow through the TRPM8 channel. Procter & Gamble and other companies have sent their chemists into the lab to design more powerful menthol analogs. Here's an example of one that was patented by Procter & Gamble a few years ago. And this compound is 100,000 times more potent than menthol, acting on these receptors. So if you really wanted a very cool sensation, it just takes a vanishingly small amount of this compound developed at Procter & Gamble. Okay, so cool, small molecules that are designed and built by organic chemists, or that you find in nature. Nature's molecules are usually not as potent as the best things we can design in the laboratory. But you could take your skills in synthetic organic chemistry that you learned this quarter and apply them to making this molecule that was developed by Procter & Gamble. That's the power of Chemistry 51C, and the power of organic chemistry is the ability to modulate physiological biochemical processes, cure diseases, make billions of dollars, and to do it with organic synthesis. And that's cool. Let's go ahead and get on to the topic of today's lecture, and that's electrophilic aromatic substitution. Let me just briefly check. Yeah, I always like to check to make sure that I'm recording or there's not some issue, because I've had cases during practice runs where I forgot to turn on the camera and then ended up with nothing at the end of the lecture. Here's where we left off on Wednesday. during our lecture. We've been in chapter 18 in the Gorzynski-Smith Organic Chemistry textbook. 5th edition is chapter 18. If you're using the 6th edition, that's in chapter 16. And we've been talking about how to substitute H atoms on benzene rings. The double bonds of benzene rings are typically not very reactive, but we have these very powerful 5 reaction recipes that we've been learning about that generate electrophiles that are so aggressive and so hungry for electrons that even benzene rings can attack them. But we've come across this problem where, where we talk about what happens if you already have a substituent on the benzene ring. Then where does the second substituent go? And that's really the subject of today's lecture. And we refer to that as regiochemistry, when you can have more than one possible position for substitution on your product. So I introduced you to this nomenclature where we talked about the 2 positions next to a substituent are called the ortho positions. And 3 atoms away, we call those positions the meta positions. And then on the opposite side of the benzene ring, we refer to that as the para position, or you could say those 2 substituents have a para relationship. When you take toluene, so an alkyl substituted benzene, and you subject it to electrophilic aromatic substitution, you don't get equal amounts of these 3 products. It turns out that in this particular reaction, the yields for this process are, you get 42% of this ortho product, and these 2 ortho positions are indistinguishable here. You get 56% of the para-substituted product, where the chlorine is at the bottom, and you get only 2% of the meta product. You would have a very hard time isolating that. Just by thin layer chromatography or other analytical techniques, you might not even know that was there. So really the only products you're getting here are the ortho and para products. And we refer to this tendency to get one substitution pattern and not another. We refer to that as regiochemistry. So let's take a look at how different substituents affect the rates of reaction at different positions on a benzene ring. And I'm going to start over here. We're going to take 5 canonical examples of substituted benzenes. Benzene rings that have substituents with lone pairs, in particular oxygen and nitrogen lone pairs. Benzene rings that have alkyl substituents. Then benzene rings that are unsubstituted. I've drawn an H here, but every position on this benzene ring has a hydrogen atom. Then we'll compare that to a halogen substituted benzene ring, and then finally to a ring that has a nitro group. And what's important to note here is the rates of electrophilic aromatic substitution at the different positions of these rings. Let's take a look at what happens when you have a methoxy group on a benzene ring. And you'd see similar rate differences if you had an NH2 group or an amino group on the benzene ring. The ortho and the para positions are way, 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 way more reactive than the same positions on just unsubstituted benzene. We're comparing the relative rates of substitution versus just the rate of reaction of any of the atoms of a benzene ring over here in the middle. So you can see that alkoxy substituted benzene rings are really souped up at the ortho and the para positions. But interestingly, you look over here at the meta position, and it's actually slower to substitute than a benzene ring hydrogen atom. So if you were to isolate the products from bromination or nitration or sulfation of an alkoxy benzene, you're only going to see products of ortho and para substitution. When we get to toluene, like I just showed you in the example above, you still see that the ortho and para positions react faster than the meta position, but they're also faster than regular benzene ring. Alkyl groups make benzene rings more reactive than just simple benzene in electrophilic aromatic substitution. So we refer to these 2 types of groups over here that accelerate the reaction of the benzene ring. We refer to those as activating groups. Now let's continue down our list here and get to halogens like bromine or chlorine. Those are the common ones. When you put a bromine atom on the benzene ring, it's slower to react. It slows down the rate of reaction of the rate of substitution of these CHs. You substitute more slowly in electrophilic aromatic substitution. At every single position, it reacts more slowly than a benzene ring. but you still see a preference for ortho and para. So all of the positions react more slowly than benzene, but the meta position is way slower. So if you did electrophilic aromatic substitution on bromobenzene, you'd see that the reaction is slower, but you would still get a mixture of ortho and para products. Don't worry so much about this difference of 0.1 and 0.03. If I ask you to draw the products for substitution of bromobenzene, just say you get ortho and para and assume that it's 1-to-1. Those differences between ortho and para are not important for this class if you just have one substituent on the benzene ring. Now lastly, we come over here to the nitro substituted benzene ring. And what you can see here is that nitro group really, really slows down reactions of benzene rings. Nitro substituents, I don't even know how to, that's like, what, 100,000 times slower than the reactivity of regular benzene. That nitro group really is slowing down. And if you can add an electrophile that is super aggressive, like a nitronium ion is super aggressive enough to add a second nitro group to here, what you would find is that now the ortho and the para positions are slower than the meta positions to substitute. Now the meta position is the favored position, not because it reacts faster than a benzene ring, but because it's slowed down less than the ortho and the para positions. So let's go ahead and talk about how we can explain these regiochemical effects. Why is it that some groups slow down reactions of benzene rings, some groups speed up reactions of benzene rings? Why is it that sometimes the ortho and para positions are faster than the meta? And why is it that sometimes the ortho and the para positions are slower than the meta positions? And to explain this, we're going to have to draw a million zillion resonance structures, and you can't complain about that. That's what this chapter is about. It's about drawing millions and zillions of resonance structures. And you just have to do it. Okay, let's go ahead and talk about this, this issue of regiochemistry. I'm going to use the letter Y just to represent some generic substituent. And for the moment, you don't worry about whether I'm talking about a methoxy group or an alkyl group or a nitro group. I'm just trying to draw our starting set of resonance structures. And let's just remind ourselves of what these arenium ion intermediates look like. So if you want to understand whether some group that I'm symbolizing with the letter Y, how that's going to affect electrophilic aromatic substitution, you have to start by drawing that first arenium ion where the carbocation, the positive charge, is next to the original substituent. So when I draw this here, we're going to end up seeing that Y ends up in one of the resonance structures. Y ends up directly next to this carbenium ion, this positive charge on a carbon. That carbon has only 6 electrons. It doesn't satisfy the octet rule. And so if you put substituents right next door, it's going to have a strong effect on that carbon atom. So in this case, the substituent Y, any substituent that you have on the benzene ring, if you substitute ortho at the ortho position, then the Y substituent will strongly affect addition to the ortho position. There's a very strong effect. But now let's contrast that with the effect of adding the electrophile to one of these two metacarbons, either here or here. So instead of adding to the ortho carbons, what happens if we add the electrophile, to one of the, I'm going on to the paracarbon. What happens if we add the electrophile to the paracarbon? So let me go ahead and start drawing these resonance structures. So as soon as we take the electrons away from this paracarbon, or sorry, this metacarbon, and leave behind this carbocation, there's another important resonance structure that we can draw. And let me go ahead and draw that resonance structure. And you have to get ready to just draw a lot of arenium ion resonance structures. If you glance through the chapter, they're drawing resonance structure after resonance structure after resonance structure. And I've already messed this up because I'm trying to talk at the same time. Let me go ahead and start by drawing these resonance structures. This is the key resonance structure. I'm going to take these electrons and attack that carbenium ion, and it's going to leave behind the carbocation right next to the Y substituent that was originally on the ring. And so you can see, if you substitute here at the para position, that Y group is going to strongly affect addition. Because this Y is right next to this carbenium ion in one of these two resonance structures, that same Y substituent is going to strongly affect. I'm trying to make this thing like point to this carbocation position. So if you add para, Y strongly affects addition para. Because in one of the resonance structures, the Y substituent ends up right next door to a carbon that only has 6 electrons. So you can expect that that carbon that only has 6 electrons is super angry, and it's going to be strongly affected by, by the Y substituent. Okay, let's get down to the meta position. Notice that the arrow pushing for substitution at the para position and the arrow pushing for substitution at the meta position is exactly the same. You use the same arrow that starts from the middle of the double bond. Be precise about that. You can't tell from my arrow pushing whether I'm going to add this E to the para position or the meta position. So the arrow pushing is the same. It's not till I draw this next intermediate that you know whether I was taking electrons away from the para carbon or the meta carbon. Okay, so let's go ahead and start thinking about this. Let's go ahead and start drawing resonance structures. Is there going to be a resonance structure where this carbenium ion, this carbocation is next to the Y group? Let me start drawing some resonance structures for that. I'll take electrons from this double bond and donate them into that poor carbon that only has 6 electrons. Let's see what that first, or maybe I should say that second uranium ion resonance structure looks like. Okay, so the carbocation is not really right next door to the Y group, right? It's not over at this position right here. The carbocation is one carbon away. Let me draw another resonance structure. I'll shift this double bond over, and I'll draw the third uranium ion resonance structure. I don't want my Y to, try to make sure my Y doesn't look like it's directly attached. So you can see in this third uranium ion resonance structure, in fact, in none of these uranium ion resonance structures for meta substitution does the Y group end up directly attached to the carbon that only has 6 electrons. And so that means that the Y does not, if you substitute at the meta position, that means that the Y group here does not strongly affect, addition meta. And let me distinguish this one up here and write down para. So if you substitute either ortho or para, the Y substituent will have a strong effect because one of the resonance structures puts the Y right next to that carbon with only 6 electrons. But when you substitute meta, the Y does not have that strong effect. And so let's see how this plays out depending on what is the nature of Y. You need to get used to drawing bunches of resonance structures. That's really the key here. Okay, I'm going to start by drawing some of the resonance structures that you would get if you substituted a benzene ring that had a nitrogen substituent on there with a lone pair. So if you started off with an amino group or an N,N-dimethylamino group, any kind of an amino group where there's a lone pair on the nitrogen atom, if you substitute at the ortho position, let's suppose you added a substituent here at this ortho position, you're going to get a resonance structure. One of the 3 uranium ion resonance structures that you get would put this carbocation center with only 6 electrons right next door to a nitrogen that has lone pairs. And that nitrogen, when it's in that position, can strongly stabilize that carbon atom. It can donate electrons into that carbocation and really satisfy that unhappy carbon that only has 6 electrons. There, you get another, a similar looking arenium-ion resonance structure when you substitute at the meta position. You find out that the amino group is able to strongly stabilize one of those arenium-ion resonance structures when you add to the meta position. So when you add to the meta position and there's any kind of a nitrogen with a, or an oxygen with a lone pair, in those cases, you get very strong stabilization. So strong stabilization. These are kind of similar in terms of the level of stabilization that you get. That means it's faster to add. That's why it's so fast to add when you have nitrogens with lone pairs, oxygens with lone pairs, O alkyl groups, O methyl, OH, N with 2 alkyl groups. Any one of these types of atoms that has lone pairs here will accelerate addition to the ortho and the pair positions. And the more strongly donating those lone pairs are, the faster it will be to add to the ortho and pair positions of those types of substituted benzenes. Now, similarly, if we have an alkyl group that has no lone pairs, we're still going to see stabilization. So let's go ahead and draw out those arenium-ion, some of the key arenium-ion resonance structures. So if I have an alkyl group here, I'll just put an R group. That could be methyl, it could be ethyl, isopropyl, T-butyl, just some alkyl group carbon atom with no lone pairs on there, and just H's, CC bonds or H's. So when we draw this arenium-ion resonance structure, there's 3 possible ones, but I'm going to draw the key arenium-ion resonance structure that puts a carbocation right next to the R group. There's 2 other arenium-ion resonance structures in addition to this when you substitute at the ortho position. I'm drawing the one that puts the carbocation next to R because you can see that this is a tertiary carbocation. And if I draw the arenium-ion resonance structure with a carbocation down here at the meta position or a carbocation at the pair position, the R group doesn't have a big effect there. But because of this resonance structure, it's fast to add at the ortho position because you end up with a resonance structure that's a tertiary carbocation. You should also expect that if you add your electrophile, if there's an R group on the benzene ring and you add your electrophile to the pair position, we're going to end up with one of the 3 possible arenium-ion resonance structures that is also a tertiary carbocation. So these are strongly stabilized. I'll say not as strongly as a lone pair, but tertiary carbocations are more stable than secondary carbocations. And so these have the same type of stabilization. They're kind of like tertiary carbocations because look, that positive charge is on a carbon with 3 substituents. So they have the same type of stabilization. They're stabilized kind of the same amount when you substitute at the ortho or the pair position. When you have a propyl, an isopropyl, a T-butyl, all of those prefer to substitute at the ortho and pair position because one of the resonance structures for the arenium ion looks like a tertiary carbocation. So things with lone pairs, and then alkyl groups. They don't have lone pairs, but they still favor ortho-para substitution. Now let's contrast that with groups that don't have lone pairs. And groups that have maybe partial or full positive charge character on them. This is going to be a completely different story. So now, when I take a look at substitution of, we're going to start out with this, what's called an ammonium ion. It's got a nitrogen, but there's no lone pairs on that nitrogen. When we get to chapter 25 on amines, we're going to spend a lot of time talking about ammonium ion compounds. An ammonium ion has a positive charge on nitrogen. An oxonium has a positive charge on oxygen. A sulfonium has a positive charge on sulfur. So when you hear me say ammonium, you know that there's no lone pair on the sulfur and there's a positive charge on the sulfur. So let me go ahead and draw out one of the key resonance structures for electrophilic aromatic substitution. If you tried to substitute either ortho or para, I'm only going to draw out the ortho one here, when there's one of these types of atoms there, and I'm going to use this ammonium ion as the example, right? The difference now is there is no lone pair on this nitrogen. And so when you put a carbocation next door, it's not just that there's no lone pair. Not only is there no lone pair, but you've got two positive charges directly next to each other, which is just crazy. That is so unstable. That is so crazily unstable. You would never want to substitute at the ortho position. Now, I'm not going to draw it out, but if you tried to substitute at the pair position, you'd end up with another one of these crazy looking resonance structures that just looks completely unhappy and unstable. So this problem of all of these substituents, N with no lone pairs, N with no lone pairs, sulfur with no lone pairs, carbonyl with no lone pairs, we'll talk about that in just a second. All of those really, really destabilize substitution at the ortho and the pair positions. And so you're left with meta substitution by default, right? It's that they slow down. Substituents that don't have lone pairs, except for alkyl groups, favor meta substitution. So you don't want to end up with these destabilized. This is, let me just say, unstable, just crazy. Right? Don't substitute ortho and para when you have one of these because it destabilizes. That substituent then destabilizes these uranium ion intermediates. Okay, I want to take a look at this carbonyl group here because it's a carbon atom that has no lone pairs. And so why is this so different from an alkyl group? And let me go ahead and draw out a resonance structure for a benzene ring that has a carbonyl group attached next door. Anytime you have carbonyl groups, and we're coming up to this in chapter 22, anytime you have carbonyl groups, there's an important resonance structure for that carbonyl group. And that important resonance structure puts negative charge on oxygen and positive charge on carbon. So that's an important resonance structure for any carbonyl. And that's why when we get to chapter 22, we're going to be adding nucleophiles into the carbonyl carbon atom over and over and over. One nucleophile after another, we're going to see that it adds to this carbonyl carbon. That's how important this resonance structure is. So if we tried to substitute at the ortho position of a benzene ring that has a ketone next door, or an ester next door, or an acid chloride next door, or an aldehyde next door, any kind of carbonyl, we're going to find that that's incredibly destabilized. So if you add an electrophile of some kind to a benzene ring that is a carbonyl derivative, you'll get this very unhappy resonance structure if you try to add to the ortho or para position. So let me draw one of those resonance structures here for you that you would get if you substituted the ortho or the para position. And so we would end up with this uranium ion resonance structure once again. There's no lone pairs on that carbon atom right next door. And so what you would find is that that's strongly destabilized. And that's why if you have carbonyl groups attached to your benzene rings, you don't want to substitute ortho or para. It destabilizes that. Okay, so alkyl groups and carbonyl groups are completely different in their character. Alkyl groups activate. Alkyl groups favor ortho-para substitution. Carbonyl groups deactivate benzene rings, and they disfavor ortho-para substitution. So, and by default, we'll say meta substitution is preferred, but it's really that, that ortho and para substitution are disfavored. I want to come back and talk about one of the most confusing issues in organic chemistry. And I feel like maybe the book in some way has contributed to this confusion. And I want to talk about this conundrum. I'm not sure really how to describe it. And that is that electronegative substituents that have lone pairs have two possible effects on adjacent atoms. And I'm going to talk about those two effects. One is an effect that's caused by the electronegativity of that substituent. Could be oxygen, could be nitrogen, could be a halogen atom. And the other effect we're going to talk about is the effect that's caused by having lone pairs on that substituent. And it's these situations where you have both a lone pair and the atom is electronegative where you're going to be caught trying to figure out which effect is more important. So we'll talk about the smaller effect first, and that is that electronegative atoms destabilize carbocations. So oxygen is electronegative. If you look at the periodic table, you know, it's more towards the, I don't know how to, it's more towards the upper right-hand corner of the periodic table. It's more electronegative. And so because of that, right, this electronegative atom will destabilize this carbenium ion. And likewise, if I draw an arenium ion that has an alkoxy substituent on there, it is true that that electronegativity effect is causing a little bit of destabilization. There's some sort of a polar effect there where, you know, oxygen has more protons in the nucleus, and all those positive charges in the nucleus make it really unhappy to be next door to this carbon that's only got 6 electrons. But now let's take a look at the other effect, and that is the effect of the lone pairs, which I've highlighted. Let me make those a little bit more red so you can see them. They're powerful donors. Lone pairs stabilize. The electronegativity of the atoms destabilize adjacent carbocations, but lone pairs strongly, let me put strongly, stabilize carbocations through resonance donation. So if you ever make a carbocation that has an oxygen next door, you can draw a resonance structure that looks like this. This is called an oxonium ion when you draw this resonance structure. This resonance structure would be called a carbenium ion. You don't need to really know that nomenclature, but this resonance structure is amazing because if I count up how many electrons are on this carbon atom in this resonance structure, it's 2, 4, 6, 8 electrons. This carbon atom now satisfies the octet rule. That's the most important driving force in organic chemistry. It's the octet rule for second row atoms, not charge and electronegativity, but the octet rule. The oxygen may have a positive charge. That's not good from an electronegativity standpoint, but it still satisfies the octet rule. There's 2, 4, 6, 8 electrons on that oxygen. It satisfies the octet rule. So having lone pair donation greatly stabilizes carbocations, more than primary, secondary, tertiary, more than any of that. So when you have a benzene ring, right, when you have a benzene ring that is getting substituted at the ortho or para positions, having an oxygen substituent next door is hugely stabilizing because one of those arenium ion resonance structures, maybe I better draw both of those resonance structures. One of those arenium ion resonance structures can be drawn such that the carbon atoms in the benzene ring all satisfy the octet rule. So here's that other resonance structure that we usually draw, this arenium ion resonance structure, but that's not the really amazing resonance structure because look, that carbon at the top of that arenium ion still doesn't satisfy the octet rule. But now when I draw this, that carbon atom now satisfies the octet rule. So there's two effects of oxygen's substituents on benzene rings, nitrogen substituents with benzene rings. If they have a lone pair, the stabilizing effect of the lone pair wins out, not the slight destabilization caused by the fact that oxygen or nitrogen is electronegative. And there is no way that you could have known which was going to win out without me telling you on this slide during this lecture. That's important for you to remember. So it's the satisfying the octet rule. The octet rule is such a major driving force in organic chemistry. Okay. Boy, when you have substituents in arenium ion intermediates, and those substituents are right next to the carbocation, they have a strong effect. Here's a summary of the effects that we've kind of talked about. If you start off with a substituent on a benzene ring, if you have any one of these substituents here on the benzene ring, what we've done is we've ranked these in terms of which ones slow down the speed of substitution, which ones make it slower for electrophiles to add to the benzene ring. So these are all substituents. We're not talking about nitrating a benzene ring. I'll come to this in a second. But if this is a substituent that's already on the benzene ring, what's the effect on adding another substituent? So if you have a nitro group on a benzene ring, it's going to slow down the next electrophilic aromatic substitution. If I come back up here, if you have an amino group on a benzene ring, electrophilic aromatic substitution on that benzene ring occurs much faster when you add the second substituent. So we call these groups that are faster, that react faster than benzene, right? So in other words, we're talking about groups attached to benzene rings where this is something here. So amino groups are way, way faster than benzene rings that just have an H here. Alkoxy groups are faster. All of these groups here are faster. Phenyl groups will speed up rates of electrophilic aromatic substitution because double bonds can donate into carbocations through a allylic or benzylic resonance. So all of the groups up here we refer to as activators because they cause benzene rings to react faster when these are substituents on those benzene rings. Everything below the H, halogens, carbonyl groups, sulfonyl groups, ammonium ions with no lone pair and a positive charge, nitro groups, all of these are deactivators. They slow down the addition of the next substituent to the benzene ring relative to just simple benzene. You have to memorize this. Now, let me just say, you absolutely have to memorize this ranking. You're not going to be able to just rationalize this ranking based on first principles. So I promise you that every section of Chemistry 51C, you're going to be asked questions that require you to know how these are ranked. And there's no shortcut there. You just simply have to memorize this ranking. All right, so memorize that ranking. We'll end up using that to solve problems. It's a powerful problem-solving tool once you've memorized the ranking of those substituents as activators and deactivators. Oh, I have to come back. I think I forgot to tell you one of the most important distinctions. I didn't finish. Let me come back to this. You know, we mentioned how these substituents affect the speed at which different benzene rings react. But what I didn't come back is summarize for you what's the effect on regiochemistry. So we already mentioned that if you have something with a lone pair like oxygen or nitrogen attached to the benzene rings, the next substituent you add is going to prefer to go ortho or para. And that's true. That's going to be true for any of these substituents from halogen and above. All of these substituents are referred to as ortho-para directors. That means that the next substituent you add, if you have a chlorine on there, the next substituent goes ortho and para. If you have an alkyl group on here, the next substituent goes ortho or para. If you have an amino group on the benzene ring, then the next substituent will go ortho and para. But anything below the halogens, carbonyls, sulfonic acids, ammonium compounds, nitro groups, if you have any of these substituents on your benzene ring, the next time you do electrophilic aromatic substitution, that second substituent will prefer to go meta. So we refer to these as meta-directing groups. So meta-directors, I should say directors, because I put ortho-para directors here. So you need to memorize this breakpoint. You can't rationalize it. This chart is going to help you to solve all kinds of problems in the backs of the chapter, on my exams, on the exams in other sections. These are the kinds of questions that they traditionally ask on standardized test exams that you use to get access to medical schools. Those effects are important. Okay, this language is a little bit confusing. And I have to disentangle this language to prevent you from making a mistake. And I'm frequently going to say, use language like nitro groups are meta-directors. And I want to be clear about what that means, because if you didn't pay close attention in the lecture, it's going to mislead you into thinking something that's not true. So nitro groups are meta-directors. And so when we draw the product of this electrophilic aromatic substitution reaction, and I know that nitro groups are meta-directors, I want you to resist the temptation to do this. When we say that nitro groups are meta-directors, it doesn't mean that nitro groups always add to the meta position. That's not what that means. That's completely different from what it means to say that a nitro group is a meta-director. Let's just go ahead and cross this out. This is not what you get from this reaction here. When we say that nitro groups are meta-directors, we're talking about if the nitro group is already on the benzene ring. The product you get in this reaction, if you do nitration of chlorobenzene and you want to understand the substituent, you have to look at whether the chlorine group is an ortho-para director or a meta-director. You don't look at the reagent that you're adding, you look at the substituent that's on the benzene ring first. This is how you determine regiochemistry. So if you want to know whether the nitro group goes meta, ortho, or para, you have to know what is the directing effect of the chlorine substituent. Halogens are ortho-para directors. So the products that you're going to get in this reaction are substitution ortho and substitution para. And don't worry about whether the ratio is 60-40 or 70-30. That's not really important. Just assume it's 1-to-1 when we say something is an ortho-para director. Okay, don't get confused about what we mean when we say nitro groups are meta-directors or carbonyl groups are meta-directors. If you wanted to make this compound, you could make this compound through this way. I would say yes and no, right? But you wouldn't be able to make this compound by starting with chlorobenzene. If you wanted to make this meta-chloro-nitrobenzene compound, you need to start with the nitro group on there. Now we can take advantage of the fact that a nitro group is a meta-director. If the nitro group is there first, then the next substituent will go to the meta position. So you can see how understanding the directing effects of various substituent affects your synthetic strategy. If I tell you to make this compound from benzene and you start off by chlorinating first, you've made the wrong decision. What you needed to do is nitrate benzene first. Whoops, there should have been no substitution. What you should have done is nitrate the benzene ring first and then treat that with chlorine and FeCl3. That's the way to make a compound like this. You have to do things in the right order. Okay, so you're going to tend to get confused because the language, meta-director, makes it sound like some of these substituents, you know, have it built into themselves, whether they add ortho or para or meta. But it's really the first substituent that's on the benzene ring that determines that. You know, I mentioned that there's 5 different reactions that you need to learn for this chapter. You need to learn about halogenation with Cl2 and FeCl3, for example. You need to learn about nitration with nitric acid and sulfuric acid. You need to learn about sulfonation with sulfur trioxide and sulfuric acid. You need to learn about Friedel-Crafts acylation, Friedel-Crafts alkylation. Those are reactions you need to learn. But this Friedel-Crafts alkylation reaction is one of the least useful of the types of electrophilic aromatic substitution. And so I want to talk through all the different exceptions there are to Friedel-Crafts reactions, whether it's acylation or alkylation. It turns out that acylium ions are not the best electrophiles. Carbocations are just not the best electrophiles. So, and this recipe that we talk about with aluminum trichloride kind of presents problems with that. So let's go ahead and talk about those exceptions. It turns out that if you try to do some sort of a Friedel-Crafts reaction where you generate an acylium ion, turns out there's going to be no reaction, right? That's not going to work. Because this is not a reactive enough electrophile to react with a super deactivated benzene ring. And so it turns out that if you have any kind of deactivating group that is more deactivating than a halogen, you can't do Friedel-Crafts. I'm going to write no Friedel-Crafts. And it just so happens that this overlaps with all of the groups that are meta-directors. The simple rule that you need to remember is that if you have any kind of a meta-director on your benzene ring as the only substituent, it's going to be so deactivated that you can't add acylium ions or carbocations. You can't do Friedel-Crafts on these deactivated types of benzene rings. Now, what's weird is that there is also a problem that if you have the most activated possible group, that you also cannot do Friedel-Crafts reactions. And that's because aluminum trichloride, so I'll write no Friedel-Crafts. And that's because aluminum trichloride reacts with the lone pair on nitrogen. That lone pair on nitrogen is so reactive that the amino group complexes, forms a bond to the aluminum and won't let go. And once you take away the lone pair, it's dead. It turns into an N+, and it immediately turns into one of the worst deactivating groups once you form a bond with that lone pair on nitrogen. So you can't do Friedel-Crafts reactions with these types of amino groups. And similarly, under protic conditions, you have problems that you just simply protonate the amino group of the benzene ring. So you can't do Friedel-Crafts when there's amino groups on the benzene rings, where there's two alkyls or two H's. And you can't do Friedel-Crafts when there's any of these deactivating meta-directors on the benzene ring. Does that mean you can't make compounds like this? Yes, you can make compounds like this, but you have to be very careful about the sequence of reactions. So if you wanted to make this compound, you couldn't start with nitrobenzene because it's too deactivated to react with acylium ions. But if you wanted, and you were clever, you could first put the carbonyl on there using a Friedel-Crafts reaction, and then do the nitration reaction second. That's the way to make a compound like this. So again, if you wanted to make a compound like this from benzene, you need to very carefully choose your reaction sequence. So this understanding these limitations of the Friedel-Crafts reactions allows you to choose the right synthetic strategy that will make things work. Okay, let's talk about another issue that arises. You know, again, there's only 5 reactions in this chapter. How can it be so much work? It is a lot of work to master the material in chapter 18. It's a dense chapter, and it's all these exceptions and you've got to memorize that ranking of activators and ortho-para directors. But here's another special type of exception that you need to remember. If you take phenols, phenols are reactive. They're a little more reactive than an O-alkyl compound, but they're too reactive. If you use your traditional recipe using FeCl3 and Cl2, you can't stop after adding just one alkyl group. Right? The first halogenation may occur ortho or para, but it's still so activated that you can't stop it from adding a second time. And it'll keep adding and add a third time. You can't stop it. And you might say, well, what if I just added one equivalent of chlorine? Well, then you'll get a mixture of tri-substituted, mono-substituted, di-substituted, and starting material, but you wouldn't get a high yield of mono-substituted chlorophenol. So the problem is this FeCl3, that phenols are so activated that this FeCl3 just goes too far. So in these cases, if you want to halogenate a phenol, what you simply do is you leave out this FeBr3 in this case, or FeCl3 if you're doing chlorination. If you leave out that catalyst, then you can get good yields with phenols because they're so activated. You don't need the FeCl3 or the FeBr3. It just messes things up. So if you leave out that Lewis acid catalyst, then you can get monohalogenation. And you have to remember that you have to leave out the Lewis acid when you halogenate phenols. You just have to remember that. Okay, when we have anilines, remember they're at the very, very top. So when we have amino groups on benzene rings, they're at the very top of that activating group list. And they are so activated that no matter what you do, you're going to get over halogenation in these cases. And there's really no way to stop that. So this is kind of, this is the only product that you can expect to get when you do halogenation of anilines. When there's where there's alkyl groups or H's attached to that. A little bit different if you have a deactivating group attached to the nitrogen, but that's really mainly a topic for chapter 21, I think. Okay, so when we come back on Monday, we'll be able to talk more about what kinds of reactions can you do with these substituted benzene rings. I want you to start working problems, work problems in the book, work problems in sapling, work every single problem you can get your hands on, because you need to practice drawing lots and lots of rhenium ions to explain regiochemistry. You need to practice drawing out correct reaction sequences. You need to memorize that ranking of activators and deactivators and memorize ortho and para-directing substituents. We're going to be asking you those questions. All the sections are going to be asking about those things on our exams. And you just simply need to go out and memorize those tools and start practice using them. Don't wait until later. Get on that and stay on it. Okay, I'll see you on Monday during the lecture, and look forward to interacting with you during office hours and discussion sections.